Well, thanks everybody for joining me for my talk today. I'm going to talk about how we're using Pulsar at Iterable to scale our customer engagement platform. So here's a kind of a brief overview of what I'm going to talk about today. First, I'll just talk a little bit about me and my background, my experience. Then we'll go into Iterable and how we generally manage Scala at Iterable. Then talk a bit more about RabbitMQ, which is the message broker we've been using in the past and some of the challenges we had with it. Next, why we ended up choosing Pulsar. Then we'll dive deeper into our first Pulsar use case, which was message sends. And we'll talk a bit more about some implementation details with some code, specifically some Scala code. Then we'll talk about some bugs and lessons learned and our future plans with Pulsar. So first, a little bit about myself. I've been a software engineer at Iterable for about 2.5 years, working mostly on various internal frameworks and the messaging architecture. So you might guess that given that I'm doing a talk about Pulsar. I previously worked for a bunch of other startups, including one that I founded myself. I also helped maintain a few different open source libraries. The most popular you may have heard of is called Play Framework. I also maintain Pulsar for S, which is a Scala client for Pulsar, and Directory Watcher, which is a file watching utility, and a bunch of other smaller projects. And here I'm mainly speaking as a user of Pulsar. I'm not going to get too much into the internals and of how Pulsar works. I assume you've seen some of the other talks, so you have some context on that. And I'm going to also talk a little bit about sort of my experience with the community as an open source maintainer and sort of how I see things there as a project. So as I mentioned, I work at a company called Iterable. So what is Iterable? Well, we're a B2B startup that's building tools to help marketers, primarily at B2C companies. Specifically, we give our customers tools to build very targeted customer experiences, very targeted customer engagement campaigns to maximize the relevance and usefulness of their products to their users and promote greater engagement with their products. So ultimately, our customers use Iterable to send some kind of message to their users. So that could be through many different media, including email, SMS, push notifications, in-app notifications, etc. There's also, so here's a small sample of our over 500 customers. And our customers span a very wide range of markets. So you can imagine there's a wide variation in the ways our customers interact with our users. And Iterable's product aims to provide support for various strategies that best fit each of those customers' needs. So our large user base means that we're ultimately processing billions of events for our customers' users every day. And each of those events can have complex behaviors associated with them and trigger other events, et cetera. And these events consist of things like hundreds of millions of sends, hundreds of millions of ingested users of events, and hundreds of millions of states in customer-defined workflows every day. And that, among many, many other things we have. Obviously, with this type of scale, we want to design our system in a way that minimizes the complexity that we as developers have to deal with. And we want to save ourselves from having to actually manage the state ourselves and outsource it to some other thing. So as a result, we mostly, originally when we built our system, we designed it mostly around using shared queues for managing that state. So this diagram should give you a sense for, at high level, the kinds of things we're using queue-like abstractions for in our system. For most of these, we were originally using RabbitMQ. So for data ingestion, we ingest user updates and events into our Elasticsearch cluster so customers can use them for their marketing campaigns. We actually switched using Kafka for this quite a while back. We actually did another talk about that because that was a better fit for this particular use case than RabbitMQ. We also use queues to track the series of states the user passes through in these customer-defined directed acyclic graphs that we call workflows. And these are basically defined by the customer and can consist of a number of different custom actions like filters and including sending messages out to users given certain criteria. Also, for scheduling campaigns, we use queues to schedule jobs that actually perform the queries to Elasticsearch on either a one-time or recurring basis, and then enqueue individual entries into a different set of queues that enqueue sending the messages out to users. And also, we use queues for sending the individual messages, and sometimes we'll queue directly into those queues, for example, for a transactional email or for individually triggered marketing emails that are triggered from the API or from a workflow. So if we want to use like queues and streams to handle the state of all these different processes, we have a couple of different requirements that we want to have in our ideal system. So this is what we had for like ideally, but we didn't really know whether we'd be able to have a single system for everything, or we want to have two separate systems. But ideally, it would support all these different requirements. So one is support for ordered streams of messages. This is mainly for our data ingestion and use cases where we care about strict ordering, like we want an update for one user to happen before the update for the next update for that user. And we're currently using Kafka for this, and it works pretty well, but it would be convenient to not have multiple systems. We also want support for simple work queues, and this is probably the most common use case we have. For example, queuing, sending an email, triggering a webhook, executing a step in a workflow, etc. And for that, we don't care about ordering, and we mainly use RabbitMQ for that until recently, and in a few cases we've used SQS for it. We need high availability, so we want to minimize the downtime we would have and be resistant to any types of failures in the message broker, so our state doesn't get lost. We want support for delayed work functionality. So we want to say we want to delay some queue item to be processed at some time in the future. So that can be used for a few different things. For example, we might want to retry a task or in a few minutes and with some slightly different parameters, so we'll republish the message with some modifications. Or we might want to send a message to a user after some required delay, and it's convenient if the queue system can support some sort of delay to do that for us automatically. We also want to support many separate queues. So this allows us to segment by customer and additionally by different types of messages with different priorities. So our system, the reason for this is our system provides a lot of flexibility, and that includes the ability to make very expensive dynamic queries to Elasticsearch and other things that can be expensive. And we want any slowness for one customer to not end up delaying work that we're doing for other customers. Doing this can require up to 10K queues per service and sometimes more, depending on the strategy we use for those queues. And we have at least 10 services, and that number is kind of growing as we scale our system. We also want to support different rate limits, so that it's helpful to have separate queues so that we can have a different rate limit on each queue. So we've been using RabbitMQ for work queues up until recently, and we've had some pretty serious issues that have caused us to really reconsider whether it's the right solution for our needs. The most common issue we've had was with memory use, causing the queues to go into flow control, which would block our publishers. And this kind of defeats the purpose of having the queue system in the first place, because if I'm a producer, I have to figure out what am I going to do with that state until the queue is actually ready to accept the message. Also, in order to support delayed messages, we actually used a technique where we set an expiration time on the message where it would dead letter into some other destination queue. And this is actually a pretty common technique, but RabbitMQ isn't designed to support this in scale. And one of the reasons is because actually the flow control mechanism I just mentioned doesn't happen when those messages expire into some other queue. So we've had to develop workarounds for this, where if we have big batches of messages, we'll schedule jobs to shovel them from one queue to another, and that's just created additional complexity that we have to manage. We've also had problems with large numbers of queues, so we're pushing 10,000 on a single node, and that starts to cause memory use problems and stuff like that. And this made it hard to conveniently segment our load between customers and message types. And we've had issues in particular with the management interface for RabbitMQ slowing down when the queue count gets very high. It's also hard to add capacity when scale requirements change because RabbitMQ isn't built as a distributed system by default. So also, RabbitMQ doesn't really supports clustering, but doesn't really support it in a really nice, useful way. One thing I want to mention is it doesn't support network partitions that well. So, and there's also a number of other situations where we've, in our experience as developers that have used RabbitMQ, there's a high probability of losing messages when different types of failures occur. The image here is an example I found of a RabbitMQ error message when a network partition is detected. I actually think the wording of this message may have changed slightly, but I think it's kind of funny because it basically says that you shouldn't run RabbitMQ on networks that can experience partitions, which is pretty it's not a super common thing, but it's something that I think all systems should be able to think about and handle in some way. So for this and many other reasons, we've actually avoided using clustering and we have split our traffic among many non-replicated RabbitMQ nodes. And this is obviously not ideal because it introduces single points of failure. So we started looking at different alternatives for a search for an alternative to RabbitMQ. One that we looked at was SQS, which we are already using in a few minor use cases. Obviously, one downside there is that it couples us to AWS, and it kind of limits our control a little bit there. Also, it supports delays, but only up to 15 minutes. And we also thought the max payload size of 256K could be problematic. I think there were some other reasons, but those were two major ones that caused us to not use SQS. And another solution we considered was Kafka. And actually, it's pretty common to see people re-architecting their systems that use queuing to work with the streaming semantics that Kafka provides. And we were concerned there with the amount of complexity of actually supporting those semantics compared to something that supported real queue semantics. And it turned out to be a lot more work for our relatively small team to do. And also Kafka doesn't support things like delays and doesn't, at least at the moment, doesn't support as many topics. So why did we end up choosing Pulsar? Well, Pulsar needs a modern messaging system that can support thousands of customers, each with hundreds of millions of active users. Effectively, that means we're dealing with in the billions of separate users in our system. And that number will keep growing and potentially multiplying by several times as we grow and get newer and larger customers. Apache Pulsar supports our scale requirements pretty well. It can support 1 million or more topics with built-in multi-tenancy and makes it easy to add storage capacity by adding book keys and scale throughput by adding partitions and brokers. So we can scale up our cluster as we add new use cases for Pulsar. And in terms of features, this was probably the major thing. Pulsar supports both streaming and work queue semantics, along with features we need like negative acknowledgements and built-in support for message delays. And this is all conveniently packaged into one system, so we can use Pulsar for many different requirements as a replacement for our use cases for both Kafka and for our use cases for RabbitMQ and also SQS and other queue systems we're using. So basically, you could say we chose Pulsar because it had the right combination of features and scalability. So now I'm going to dive a little bit deeper into a specific initial use case, which was message sends. And I'll talk about how we use some different Pulsar components to support our needs and to migrate this from RabbitMQ. So Iterable needs to support many different send patterns. One case is that a customer has millions of users to whom they want to send the same campaign. And to do this, we'll queue the message into all these messages into our send queues. We'll have a job that does that. And each message represents the job of sending a message to a user. This situation gets a little bit more complex because the send times can be determined in a few different ways. So they could be, the simple cases, we're sending a blast campaign. This is all at the same time for all users. That's pretty simple. We just enqueue all the messages all at once. The other case is we want to send at a specific time in the user's local time. And even more complicated, we might want to have a per user send time. So we're working on a machine learning feature called send time optimization that tries to find the optimal time for each user. And we want to actually enqueue each message and say, schedule this for this particular time. In other cases, customers want to send based on a trigger, for example, an API call, or like in a workflow, which we talked about earlier. We might want to trigger a message from the workflow, and that's a common case for, like I mentioned before, like for transactional emails, like if you have an order confirmation email, our customers use this for that purpose, and also for just triggering a manual send of a marketing email. Sometimes our customers want to have control of that, and that can also be after a delay. So we have APIs that let our customers say, send this email in an hour. And as you might guess, these send times can be set pretty easily using the delayed send functionality built into Pulsar. We also needed to be able to handle intermittent failures. Like, for example, when we're sending an email, there could be a transient failure with the email service provider, and we want to retry that message. So that can either be done through negative acknowledgements, where we just knack the message and then Pulsar will automatically retry. Or in some cases, what we'll do is we'll republish to the queue after some delay with some like modification to the message. And since customer load can vary quite widely, we want to be able to scale up and down consumers easily. This works pretty cleanly with a Pulsar shared subscription, so that wasn't a huge problem. Also, to support higher throughput on the Pulsar end, we can add partitions to the consumer to scale the consumer as needed. So for each customer, we could add like if one customer has a high amount of load, we can have 4 partitions or 8 partitions rather than a single one partition. But for the most part, we found one partition works quite well and gives us the throughput we need for the vast majority of our customers. So I'm going to get a little bit more into the implementation. So when using Pulsar, we chose to make some specific choices on our application side to give us the maximum flexibility. For our topics, each service gets its own tenant. So for example, I'm going to dive specifically into email. So for the email service, we'd have the email tenant, and our namespaces would be set up by customer-specific projects. And this allows us to apply permissions and limits on the namespace level and more or less limit the resources by customer. Then we can have many topics under that namespace for different types of things that a customer might be doing on that service. For example, we might have, we might decide in some cases to have per campaign queues, or we might have queues for different message types, like a queue for transactional message, etc. We also chose to use the regular expression-based consumers that Pulsar provides. This is something that I think it gave us a lot of flexibility, especially when combined with Pulsar's auto deletion functionality. So that allows our producers to choose specific schemes for different message types in the system, and our customers can simply listen, or consumers can listen on all the topics in that namespace without having to create new consumers when the topics get created. And it's just kind of automatic. Especially nice about that is in Pulsar 2.5.1, we can, even though there's a subscription on that topic, Pulsar will still auto-delete those topics once they've gone out of use. So, for example, if we want to have a really, really large email campaign, like above a certain size, we can say we want to make a dedicated topic for that. And we don't have to worry about those topics sticking around once the campaign is finished sending. So in order to use Pulsar, we had to make several choices around tooling on our application side. Since we're mainly a Scala shop, we wanted an idiomatic Scala client. We started using a client called Pulsar for S, which is currently the most popular open source Pulsar client for Scala. We started contributing some improvements to that library, and I actually have become a relatively active maintainer in that process. One change that we added in particular was the Akka Streams-based consumer that has acknowledgement support. That allowed us to use Akka Streams to consume messages, which more closely match the style that we were using on other parts of our system. We also worked on improvements to Pulsar for S to support newly added features on both the producer and the consumer side. Pulsar for S is also nice as it integrates well with lots of different libraries in the Scala ecosystem. So it integrates with different effect types. So it works with like things like ZIO and Cat's effect, and also with several, like all the different JSON libraries that exist in Scala, and also with Avro for S to generate Avro schema as a compile time. Here's a more detailed example. I know not everyone here is a Scala developer, but I wanted to just showcase how easy it is to use Pulsar for S to create consumer and listen on topics. This is a simplified version of the code we actually use in our actual code base. So as you can see, it will create a consumer for all topics in the namespace for a hypothetical email service. In reality, we'd want to do this type of thing across all of our customers. This is just a simplified example. Then we'll create the source that receives messages from the topic as a reactive stream. And the stream handles the messages with some predefined parallelism. And after processing each message, it'll call the ACK or NACK method on the message to decide how to handle it. And schema generation can be delegated to Avro for S for Avro, or several different Scala JSON libraries. And the nice thing was, like, fortunately, Pulsar's Java APIs, actually there's a few bugs we found in this, but now Pulsar's Java APIs make it relatively simple to implement and generate schemas yourself, as long as you adhere to some standard formats. So the nice thing is now we can use Scala-based solutions to generate Avro schemas at compile time, rather than use the runtime reflection-based schemas that are built into the Java client. So it gives us an additional layer of type safety that most of the time, if you're using Scala, it's kind of expected to be there by default. A lot of the development of Pulsar for S has been driven by our needs, but we want to make it as full-featured as possible. So we definitely appreciate any feedback that people have, and especially contributions to the library. So I want to talk a little bit about our migration plan. So before we migrated Sense to Pulsar, we wanted to have a robust testing regime to build our confidence in Pulsar as a service. This was really important because we wanted to use some newer features like negative acknowledgements and delayed messages, which hadn't had the chance to be tested extensively in the real world yet. So we did some functional tests and load tests in a staging environment. And after doing that and building some confidence, we wanted to start testing production load. And we started first by making what we call test publishes to test the load and understand the behavior under the exact production load patterns. So whenever we published to RabbitMQ, we would also publish to these test Pulsar topics. And we'd have the Pulsar consumer on the other end simply act the message or do some fake processing, adding things like random delays and random failures, so that we can kind of see how it behaves. And we ran this for a few months, and we gradually ramped up the traffic, and we looked at metrics and tracing data to understand what was actually happening with those messages. And this actually allowed us to find a few issues before they surfaced in an actual production incident for us, and without having to worry about replicating production patterns and staging. We also, so to do this, we actually had feature flags to enable publishes to either the test topics or the real topics on a per customer basis. That also made sense because we could migrate customers based on their risk tolerance and various other factors. So now I want to talk a little bit about the bugs and issues that we found. So through this testing process, we found a few different issues. Well, first major one was a race condition with the delivery of delayed messages. This was actually found, we were working with Streamlio at the time, and the actual problem was discovered by them after we reported some issues with the consumers not consuming. And they helpfully fixed the issue in a pull request once they identified it, and it hasn't really been an ongoing problem. But for us, it kind of goes to show that we were right to suspect that some issues might happen, especially when we're using new features. There's also an open bug related to the use of negative acknowledgements with message batching. So when you call negative acknowledge on the message, the entire batch actually gets redelivered. So that resulted in some unexpected duplicate messages for us. Fortunately, our send services were able to detect those duplicates, so we were able to avoid customer impact because we had other mechanisms for dealing with those duplicates. And this issue happened because the message batching in the producer, which is actually enabled by default, effectively causes Pulsar to treat messages produced as a batch as a single unit inside Pulsar. So that causes some other interesting issues, like the backlog being recorded in terms of number of batches instead of the number of actual messages, which can make monitoring a little bit more challenging. And ultimately, we decided to work around this by just disabling batching. But I think this is a really significant area where we feel Pulsar's documentation could be clarified, especially since this is enabled by default. The batching is enabled by default, and the current behavior doesn't always match what users would typically expect. In addition to that, on the metrics side, another thing we thought was missing was a non-delayed backlog metric. So it turns out that sometimes taking total backlog minus the delayed messages on the subscription doesn't always give you an exact value, and that can lead to us thinking that we might have stuck messages on that subscription. In general, we think that documentation and like user experience for Pulsar is a great place for the team to focus their improvements. I mean, we kind of expected that this being an actively developed project, it's going to be kind of a bumpy road, but that would be, I think, a great thing for adoption. We've made a few improvements to the docs to help out with that. There's just a lot of different configurations for Pulsar, and it's just frustrating to have to read the docs and find something, think you can implement something in a particular way and then have it turn out doesn't work for one reason or another because there's an undocumented edge case or because it's oversimplified in some way. Another example actually that I'm thinking of now is lack of support for shared and key shared subscriptions on compacted topics. I don't think that's mentioned anywhere in the docs. So fortunately, we've found the Pulsar community to be very helpful though in answering the questions we've had that might not be clear from the documentation. So after we tested for several months and worked out some bugs, our experience overall ended up being quite good, and at the end was relatively incident-free. Overall, this reduced our current infrastructure costs required to get the same throughput. This is partly because we had to over-provision our RabbitMQ infra to work around some of its issues, and we think we'll be able to improve those costs even more as we share the same Pulsar cluster for other use cases. I didn't put a number here specifically, but I think we'll probably be able to do like 2 to 3x reduction in costs eventually. We've been running Pulsar for about 6 months in production without many issues really, and are pretty happy with it. So now that we have a solid system working for message sends, we're expanding our use cases to other parts of our system where we're currently using RabbitMQ or Kafka, including their data ingestion, webhooks, analytics, workflow execution, etc. Overall, we've learned a lot about Pulsar through our experience, and the issues we had, like I said, were not completely unexpected given that the project is in such active development. And in the end, we feel we came out very, very much ahead of where we might be with alternative solutions that didn't have the specific feature set that we wanted. And again, like the Pulsar community has been very helpful and seems to be very active, and that gives us a lot of confidence that the project is moving in a good direction and is in good hands. So we'd like to also continue our contributions to the open source community, especially with Pulsar for S and providing better tooling for Scala developers. And we really hope that more people will join us in that effort. So that's it. Thanks for listening to my talk. I hope you learned something interesting. So now I'm ready to answer questions. Also, I'm on the Apache Pulsar Slack group, so if you want to ask me any other questions, you can feel free to reach out to me, and I'm also on Twitter and GitHub. So let me see what questions are here. Some of these look like they're from the last session. I'm trying to figure out which ones.
Oh, here, sorry, let me.
I'm trying to figure out which ones are from my session and which ones are from.
Yes, I think yours should be starting with Jesse Anderson at 10:14.
I see, okay. Are you going to use the new scheduled messages to send emails, or are you going to use another system? So that's what we're using. We're using scheduled messages. So for actually sending the emails, we we use like other ESPs to send it. So customers can define their own ESP, or we might just use Amazon SES. Like by default, we'll use SES. But there's a lot of other work that we have to do, like in rendering the email from a template. So sometimes that can involve fetching other data. So that's what we're queuing up, is a job for doing that process of rendering the email and sending it off to the ESP. And we do use Pulsar scheduled messages for that. So if a customer wants to do a delay, we will, if a customer says, send this email to this email address in 2 hours or at a specific time, then we will use Pulsar for that. So I hope that answers your question. If not, feel free to follow up here. Can you share what were your pain points with RabbitMQ and what were they solved by switching to Pulsar? I think this was probably asked relatively early in the presentation. I think I pretty much shared the pain points, which were mainly just like the issues with flow control were a pretty big concern, and just memory use in the RabbitMQ cluster and things crashing, and that hasn't really been an issue with Pulsar. I think specifically, a lot of it was related to the way we do delayed messages in RabbitMQ, and the fact that that system just isn't, like, RabbitMQ isn't really designed to be used that way. Even though it seems like it's a pretty common technique. I'm not sure if there's any other specifics I can cover, but if you have specific things you want to ask about, feel free to follow up. How did you handle ACK on original message and publish as new delayed message in case of failure without TX support? So you're right. So this is something where we don't. So if we had transaction support, that would be very helpful for us. In our case, we were comfortable with not having transaction support and just assuming that if there's some cases in which those messages, in very rare cases, could get lost, and we would end up not sending out a message. But that specific requirement can differ based on the specific service we're using. We definitely would like to use transaction support when it's available. Our existing system with RabbitMQ did not use any sort of transactions, and we know that there's a possibility of messages getting lost in certain scenarios, but we designed it. And generally, most of our systems are designed to prefer not sending an email over sending an email. So that's kind of how it's designed. So, but we definitely will want to use the transaction support. So, I guess I should be pressing answer live when I'm answering it. Yeah, and I think this is pretty much the same question. How did you manage exactly once for email, avoiding sending emails twice? Oh, so another thing that we use is we have a Redis cache. So if we receive a message, we will check. We use Redis to basically do both locking and as a cache to make sure that we don't resend. So that lasts for like a day. So if we have, for example, like a common use case is like something failed in sending a campaign, so we could actually completely retrigger that campaign, and we'll just check Redis and say, is it here? Is this message? Has this message been sent? And it won't be resent because we've seen that it had already been sent. So, and actually we use Redis as kind of an additional backstop in many different parts of our system to handle if something failed in an unexpected way. Then we will check Redis and make sure that we don't resend it. What happened when you bottleneck Pulsar due to shared subscription? Because partitioning the topic prevents GUs. I'm not sure that's true. So I'm not sure what the question is there. So we don't use we don't need, like, you can still use shared subscriptions on topics that are partitioned, as far as I understand it. It's we haven't had problems with doing that specifically, but most of our topics are not partitioned. Are you running on KS? So we are. So actually, we are running on. We've been running on Amazon EKS, and so our infra team is pretty small, and we don't. We actually won't. We've been outsourcing it to other companies. So originally we were using Streamlio, and then when they got acquired and we couldn't use them anymore, we switched to using Stream Native, and we have that's basically running on our infrastructure on a shared AWS account, and they're managing it for us. But we control kind of how it's set up, and so the advantage there is that we kind of can eventually switch to managing it ourselves. And yes, it's being run on Kubernetes, and that was mostly not something that is kind of based on the recommendations of Streamlio and Stream Native. Was BK easy to operate? I can't really answer that very directly because we're not really managing it completely ourselves. But we haven't had any specific bookkeeper issues, so I'm not sure I can really elaborate too much on that.